You type out a quick text, tap send, and your message appears on a screen thousands of miles away in a fraction of a second. It feels seamless, like there's a direct, invisible wire connecting you to your friend. But that direct line is an illusion. In the early days of telephone networks, a literal, continuous copper circuit had to be held open for your entire call. Today, if we tried to send digital data over a single continuous line, the slightest network hiccup would destroy the whole file. So engineers devised a completely different approach: packet switching. Instead of sending your message as one large chunk, your device shatters the data payload into hundreds or thousands of uniform, bite-sized fragments called packets. Each one gets stamped with its own sequence number. By breaking a single message into a swarm of independent, highly mobile pieces, your device prepares the data for a journey where no single line is guaranteed to stay open. Before this swarm even leaves your phone, it needs precise instructions. The text name of the website or app you're trying to reach means nothing to the machines that will carry your data. Your device first checks the domain name system, or DNS. Think of it as the Internet's directory. It translates a human-friendly web address into a strict numerical IP address, stamping those exact coordinates onto every single packet in your message. Next, the packets need a manager to ensure they actually survive the trip. For the reliable delivery of data, the network relies on the Transmission Control Protocol, or TCP. While some protocols like UDP recklessly fire data off and hope it arrives, TCP is meticulous. It logs those sequence numbers we saw earlier and establishes a formal digital handshake with the receiving server before a single byte is sent. Now armed with exact destination coordinates and strict delivery rules, your fragmented message is ready to navigate the largest, most complex machine ever built by humans. The journey begins as radio waves. Your packets fly through the air to your local Wi-Fi router, which translates them down into electrical signals. That router is your personal gateway to a Tier 3 internet service provider. This is the local telecom company that acts as the neighborhood on-ramp to the wider web. The Tier 3 ISP reads the IP address headers on your packets and realizes they need to go much further. It instantly kicks them up the hierarchy to a larger regional Tier 2 network. Here, packets encounter dynamic routing. Routers act like high-speed post offices, calculating the fastest paths. Notice how identical packets are diverted down completely different intersecting paths. Traveling independently, if a router detects a congested link, it scatters remaining packets across alternative routes, avoiding the bottleneck. Along the way, your data is constantly handed off between competing corporate networks through a massive, invisible web of peering and transit agreements. This global network functions through the dynamic cooperation of tens of thousands of independent corporate entities, all moving traffic at blistering speeds. To reach a destination on another continent, your packets eventually hit a cable landing station on the coast. This is the heavily guarded gateway to the Tier 1 backbone. Tier 1 ISPs are the telecom giants that don't pay anyone else for access because they own the physical infrastructure of global transit. Looking inside an operations center like this one, you can clearly see the staggering scale required to monitor their worldwide networks. Inside that coastal landing station, your packets are converted from electrical signals into pulses of light that flicker billions of times per second before being injected into submarine fiber optic cables. At the core of these cables are hair-thin optical fibers carrying the actual light signals. But as you can see, those delicate strands must be surrounded by heavy layers of steel wire and protective armor. They need that armor to survive the crushing pressure and freezing temperatures of the ocean floor. To keep light pulses from fading out over thousands of miles, high-voltage repeaters are spliced into the cable to continuously amplify the signal. We like to talk about data living in the cloud, but that terminology hides the physical reality. Global communication relies entirely on heavily armored cables resting silently in the darkest depths of the ocean. On the opposite coast, the light pulses hit another landing station, convert back to electricity, and rapidly cascade down the ISP tiers to reach the recipient's local network. But because your packets took entirely different routes to get across the globe, they arrive at their destination completely out of order. Some fragments may have been dropped along the way. In this diagram, packet number 3 is missing entirely. This is where TCP steps back in. It reads the sequence numbers, instantly identifies the missing packet, and demands the sender transmit it again. Once that final piece arrives, the system snaps everything back into perfect numerical order. The speed of transmission is impressive, but the real marvel is this instantaneous creation of perfect order out of deliberate, fragmented chaos. Your hello appears on your friend's screen in less than a second, yet the massive architecture that delivered it is surprisingly vulnerable. If a single engineer makes a mistake configuring the DNS directory, the network goes blind. Without the ability to translate names to IP addresses, your browser returns an error like this, instantly severing access to major global platforms. Physical threats are just as common. An errant ship anchor dragging across a shallow seabed or an underwater earthquake can sever those optical cables and cause massive regional outages. Despite these immense risks, the system works. Right now, billions of these fragile, fragmented journeys are happening concurrently, every single second of every day. Every search, video stream, and message relies on this millisecond ballet across continents and abysses. It is an immense, global machine that works so effectively we often forget it exists at all.